Welcome to today's episode of Innovation Chronicles. 5,500 years ago, in a workshop somewhere in ancient Mesopotamia, a potter sits before a lump of wet clay. For generations, potters have shaped vessels by hand, slowly coiling strips of clay upward, smoothing with practiced fingers, creating jars and bowls that are functional but irregular. The work is slow. A single large storage jar might take days to complete. But today, this potter is about to change everything. Before them sits a new device, a flat stone disc mounted horizontally on a vertical shaft. The potter gives it a spin. The disc rotates smoothly, continuing to turn from its own momentum. They center a lump of clay on the spinning surface and press their hands against it. The clay responds differently now, flowing under their touch as the rotation brings every angle to their fingertips. In minutes, they've created a perfectly symmetrical pot that would have taken hours before. The potter's wheel has been born, and with it, humanity has discovered the principle that will transform civilization. This moment, this simple innovation of a rotating disc seems humble, yet it represents one of the most profound inventions in human history. Not because of what it did for pottery, but because of what came next. Within centuries, that spinning clay disc would be turned on its side, attached to axles, and transformed into the wheel for transportation. That wheel would enable carts and chariots, revolutionize warfare, transform agriculture, and become the foundation for virtually every mechanical device humans would ever create. But here's what makes this story fascinating. The wheel wasn't obvious. Despite being one of the simplest machines imaginable, the wheel appears nowhere in nature. No plant grows wheels, no animal evolved them. Every wheel that has ever existed is 100% human innovation. And for hundreds of thousands of years of human history, we lived without them. Why? How did such a simple yet powerful idea finally emerge? And once invented, why did it spread to some civilizations, but not others? Today, we roll back through history to discover how early humans invented the first wheels and changed the world forever. Chapter 1. The clay that changed everything. The rivers of Mesopotamia brought life to the desert. The Tigris and Euphrates, flowing from the mountains of Anatolia to the Persian Gulf, deposited rich sediments across the floodplains, creating soil perfect for agriculture. But they brought something else equally valuable: clay. Not just any clay, but elastic, workable clay that could be shaped when wet and hardened to stone-like durability when fired. This abundance of clay shaped Sumerian civilization in profound ways. By 4000 BCE, the Sumerians had become master potters. They needed to be. In a society transitioning from nomadic hunting and gathering to settled agriculture, pottery became essential. You can't store grain for the winter without containers. You can't transport water or oil without vessels. You can't cook many foods without pots. The demand for pottery exploded as populations grew and cities emerged. But traditional pottery making was laboriously slow. The coiling method, where you build up a vessel by stacking rings of clay and smoothing them together, required enormous skill and time. Each pot was unique, varying in size, shape, and thickness. A skilled potter might produce only a few vessels per day. As cities like Uruk and Eridu swelled with thousands of inhabitants, the pottery production simply couldn't keep pace with demand. The problem with shaping clay by hand is maintaining symmetry. As you work around the vessel, thickness varies. The walls bulge in some places, thin in others. Getting the shape truly round and even requires constant adjustment and smoothing. Your hands can only work on one section at a time. The clay doesn't move. You have to move around it. Then someone, and we'll never know who, had a revolutionary idea. What if instead of moving around the clay, you made the clay move? What if the vessel could spin, bringing every angle to your stationary hands? The earliest potter's wheels were simple turntables, a flat disc of hardened clay or stone mounted on a pivot. You'd place your clay on the disc, give it a spin with your hand or a stick, and while it rotated, you could shape it. This was already a massive improvement. The rotation meant you could apply even pressure all around the vessel simultaneously. But these early slow wheels had limitations. They quickly lost momentum, requiring constant respinning. The true revolution came with the fast wheel, developed around 3500 BCE. This innovation added a heavy flywheel at the bottom of the shaft, often at ground level. The potter would kick this flywheel with their foot, building up rotational momentum. The inertia of the heavy flywheel kept the upper disc spinning smoothly for extended periods, leaving both hands free to shape the clay. Imagine the transformation this created. A potter could now center a lump of clay on the spinning disc, and with gentle, sustained pressure, pull it upward into a perfect cylinder. Then, with thumbs pressing down and outward, create the opening. With fingers inside and outside, thin the walls to uniform thickness. The centrifugal force of rotation helped, pushing the clay outward against the potter's hands. In minutes, vessels emerged that were perfectly round, perfectly symmetrical, and stronger than hand-built pots because the clay particles aligned in the direction of rotation. The productivity increase was staggering. A skilled potter with a fast wheel could produce 10 times more vessels than before. This wasn't just incremental improvement, it was a technological revolution. And like all such revolutions, it had cascading effects throughout society. First, pottery became more affordable. Mass production meant lower prices, putting ceramic vessels within reach of common people, not just elites. Archaeological excavations of Sumerian sites from this period show a dramatic increase in pottery abundance in ordinary households. Second, standardization emerged. Wheel-thrown pots could be made to consistent sizes and shapes. This facilitated trade. A merchant could order 100 standard oil jars and receive vessels of uniform capacity. It also enabled specialization. Some potters focused on plates, others on storage jars, others on decorative pieces. Third, and perhaps most importantly for our story, the potter's wheel demonstrated a principle. It showed that rotating objects had unique properties. The experience of working with a spinning disc, of feeling how centrifugal force affected materials, of understanding how rotation could accomplish what linear motion. This hands-on education in rotary mechanics was crucial. The potter's wheel was humanity's introduction to the physics of wheels, even if they didn't think of it in those terms. But the potter's wheel solved a specific problem shaping clay. It sat horizontally, spinning around a vertical axis. You couldn't transport anything with it. You couldn't move heavy objects. It was a specialized tool that, revolutionary as it was for pottery production, had no obvious application outside the potter's workshop. For roughly 3 centuries, that's where wheels stayed. From approximately 3500 to 3200 BCE, wheels existed only as tools for making pottery. Thousands of potters across Mesopotamia worked with spinning discs daily, but apparently, it didn't occur to anyone that the same principle could revolutionize transportation. Why not? The conceptual leap required was actually enormous. A potter's wheel spins in place. It doesn't go anywhere. To create wheeled transport, you need to turn the wheel 90 degrees, mounting it vertically instead of horizontally. You need to solve the problem of the axle, how to make wheels rotate freely while still being attached to a vehicle. You need to understand that rolling is different from spinning in place, that wheels need to work in pairs, that they require roads or at least relatively flat surfaces. These weren't obvious problems with obvious solutions. Think about it from a Sumerian's perspective. You're familiar with sledges dragged across the ground by oxen. You're familiar with rollers logs placed under heavy objects to make them easier to move. You work with a potter's wheel that spins in place. How do you connect these concepts? How do you envision a wheel that spins while also moving forward? Someone did. And when they did, the world would never be the same. The potter's wheel was the proof of concept. It demonstrated that rotation worked, that it was useful, that it could be controlled. It familiarized an entire civilization with circular motion and the tools needed to create it. The clay that the Mesopotamians worked with such skill became the training ground for the greatest transportation revolution in human history. The potter's wheel wasn't just the first wheel. It was the school where humans learned to think in circles, where the abstract concept of rotation became tangible, where the impossible began to seem possible. And in the workshops of ancient Sumer, as potters spun their wheels and shaped their vessels, they were unknowingly preparing humanity for a revolution that would echo across millennia. Chapter 2. From spinning clay to rolling forward. Picture a Sumerian farmer around 3200 BCE, watching workers drag a loaded sledge through mud. The wooden sledge, piled high with grain from the harvest, carves deep grooves in the soft ground. 4 oxen strain against their yokes, hooves slipping, muscles bulging. Progress is agonizingly slow. When the sledge encounters even small obstacles, a slight incline, a patch of rocky ground, it grinds to a halt. Workers must unload some of the cargo, move the sledge forward, then reload it. A journey of a few miles can take an entire day. This farmer has seen sledges all his life. His father used them. His grandfather used them. It's simply how you move heavy things when you can't carry them. But this farmer has also been to the city, where he's seen potters working at their wheels, spinning vessels with impossible grace and speed. And in his mind, a connection begins to form. What if, he thinks, you could make the sledge spin like a potter's wheel? Not spin in place, of course, that would be useless. But what if you took a disc, like a potter's wheel, and turned it on its side? What if instead of the disc staying in one place while it spun, it could roll forward, spinning as it moved? This is the leap. This is the moment of insight that changed everything. We don't know who first made this connection. No ancient document records the inventor's name. No inscription celebrates the achievement. But someone, somewhere in Mesopotamia, around 3200 BCE, figured it out. The earliest transportation wheels were remarkably simple solid wooden discs with a hole in the center for an axle. They weren't carved from single pieces of wood, which would be prohibitively wasteful and difficult. Instead, they were made by clamping together 2 or 3 planks of wood with wooden crosspieces. The result was heavy, crude, and revolutionary. Creating even these simple wheels required solving multiple engineering challenges. First, the disc had to be reasonably round. A lopsided wheel would wobble catastrophically, making the cart impossible to control and rapidly destroying both wheel and axle. Achieving roundness meant careful carpentry, probably using a primitive compass, perhaps a stick with a sharp point at one end and a marking tool at the other, rotated around a central pin to scribe a circle. Second, the central hole had to be precisely sized. Too small, and the axle wouldn't fit through or wouldn't rotate freely. Too large, and the wheel would wobble on the axle, creating instability and rapid wear. The hole also had to be perfectly centered. Even slight offset would create vibration and uneven wear. Third, and most crucially, the axle mechanism had to be designed. This was perhaps the most ingenious part of the whole invention. Early Sumerian carts used 2 different approaches. In some designs, the wheels were fixed to the axle, and the entire assembly, both wheels and axle together, rotated under the cart bed. In others, the axle was fixed to the cart, and the wheels rotated independently on the axle ends. Both designs had advantages and disadvantages. Fixed wheels meant simpler construction. You just needed a strong connection between wheel and axle. But it also meant that when turning, one wheel had to slip or skid since the inner and outer wheels traveled different distances. This caused rapid wear and made tight turns nearly impossible. Independent rotation solved the turning problem, but required more sophisticated construction. The axle ends had to be smooth enough for the wheels to spin freely, but the fit had to be tight enough to prevent excessive wobble. This meant understanding tolerances, understanding friction, understanding wear. It meant developing lubricants, probably animal fat or plant oils, to reduce friction between wheel and axle. The first wheeled vehicles weren't fast. A cart with solid wooden wheels, pulled by oxen, moved only slightly faster than the sledges they replaced. But speed wasn't the main advantage. The critical improvement was load capacity. Wheels reduced friction dramatically compared to sledges. Where a sledge would stick in mud or catch on obstacles, wheels could roll over them. A team of oxen that could drag perhaps 500 kilograms on a sledge could pull 2,000 kilograms on a wheeled cart. This transformation affected every aspect of Sumerian society. Agriculture became more productive because farmers could transport larger harvests to storage facilities and markets. Trade expanded because merchants could move more goods over longer distances. Construction projects accelerated because builders could transport heavier loads of stone, timber, and other materials. The archaeological evidence for this transition is frustratingly sparse. Wood rots, especially in the damp conditions of Mesopotamian lowlands. What survives are mainly artistic depictions and a few exceptional preservation cases. One of the most famous is the Bronisus pot from Poland, dated to around 3500 BCE, which shows an incised drawing of a four-wheeled wagon. Actual wheel specimens, like those found at Ur, typically date to somewhat later periods around 3000 BCE. But even from these fragmentary clues, we can reconstruct the evolution of early wheel technology. The progression from potter's wheel to transport wheel wasn't instantaneous or linear. Different communities probably invented variations independently. Some designs succeeded. Others failed and were abandoned. The process took time. Archaeological evidence suggests perhaps a century or more of experimentation between the first potter's wheels and the widespread adoption of wheeled transport. What drove this innovation? Need, certainly. Sumerian cities were growing rapidly, creating unprecedented demands for food, materials, and goods. The existing sledge technology simply couldn't keep pace. The potter's wheel existed as a model, proving that rotation could be useful. The availability of draft animals, oxen, initially provided the power source. And the Sumerian social structure, with its temples and palace institutions coordinating large labor forces and construction projects, created contexts where improved transportation offered massive benefits. The spread of wheeled vehicles accelerated once the concept proved viable. By 3000 BCE, wheeled carts appeared across Mesopotamia. By 2500 BCE, they'd reached Egypt, the Indus Valley, and Eastern Europe. By 2000 BCE, wheeled transport had spread across most of Eurasia. This diffusion happened too rapidly to represent independent invention in each location. Clearly, the technology spread through trade contacts, migrations, and cultural exchange. But not everywhere adopted wheels immediately or at all. The transition from potter's wheel to transport wheel, simple as it seems in retrospect, represented a genuine conceptual breakthrough. It required seeing past the obvious use of a familiar tool to imagine an entirely new application. It demanded solving numerous technical challenges, and it needed appropriate social and economic conditions to make the investment worthwhile. The Sumerians had all these factors. They had the potter's wheel as a model. They had the technical skills in carpentry and engineering. They had the draft animals. And they had the urgent need for better transportation. In their workshops and fields, through trial and error, through countless failed prototypes and gradual improvements, they transformed the spinning potter's disc into the rolling transport wheel. And in doing so, they literally got humanity rolling toward a future that would be shaped, in countless ways, by circles turning on axles. Chapter 3. The genius of the axle. Here is a question that seems simple, but isn't taught. How do you attach a wheel to a cart so that it rotates freely while also staying firmly attached? This problem, the challenge of the axle, is actually harder than inventing the wheel itself. A wheel without an effective axle is just a disc of wood. The genius of early wheeled transport wasn't the wheel. It was the wheel and axle system working together. Stand up and try this thought experiment. Hold your arms straight out to your sides, parallel to the ground. Now rotate your body. Your arms rotate with you as a rigid unit. They're fixed to your torso. This is how early Sumerian carts initially worked. Wheels fixed rigidly to an axle, the whole assembly rotating under the cart as one unit. Now, try this instead. Hold your arms out again, but this time imagine that your arms can spin independently of your torso while staying attached. This is much more complex mechanically, but it's how more advanced carts worked, with wheels rotating freely on a fixed axle. Both systems require solving the fundamental challenge, creating a connection that's simultaneously firm enough to keep the wheel attached and smooth enough to allow rotation. Too tight, and friction prevents turning. Too loose, and the wheel wobbles or falls off. Get it just right, and you have a functional wheel and axle system. The earliest axles we've discovered are remarkably sophisticated, suggesting that a lot of trial and error preceded their creation. The axle itself was typically a strong wooden beam, often made from oak or similar hardwood, carefully shaped to be reasonably straight and consistent in diameter. At each end, the axle was slightly tapered or had a collar to keep the wheels from sliding off. The crucial innovation was the bearing surface, the interface where wheel and axle meet. In systems where wheels rotated on fixed axles, this surface needed to be as smooth as possible. Early wheelwrights discovered that harder woods were better than softer ones. They learned to apply lubricants. Animal fat was popular to reduce friction. They developed sleeves or bushings, often made from leather or harder wood, that fit inside the wheel hub to protect the wood from wear and provide a smoother bearing surface. Archaeological evidence from preserved wheels shows wear patterns that tell us how these early axles performed. The wheel hubs often show grooved wear in a distinctive pattern, indicating that early wheels didn't rotate as smoothly as modern ones. The friction was substantial, which is why oxen or other strong draft animals were necessary even for relatively light loads. The geometry of the wheel and axle system also mattered enormously. The axle's length determined the cart's track width, the distance between the two wheels. Make it too narrow, and the cart tips easily. Make it too wide, and it's unstable on turns and difficult to maneuver through gates or narrow spaces. Sumerian cart makers settled on track widths around 1.4 to 1.5 meters, a dimension that would become standard across ancient civilizations and persist remarkably into modern times. This is approximately the gauge of many modern railway tracks. The wheel diameter was another critical variable. Larger wheels roll over obstacles more easily and travel farther with each rotation, but they're heavier and more difficult to construct. Smaller wheels are easier to make and replace, but provide less ground clearance and get stuck more easily. Early Mesopotamian wheels were typically 0.5 to 1 meter in diameter, a size that balanced these competing demands. Perhaps the most ingenious aspect of the axle system was how it distributed weight. When a loaded cart rests on two wheels, the load is transmitted through the axle to the wheel centers. From there, it spreads through the wheel structure to the ground contact point. This means the wheel must be strong enough to handle substantial compression forces without breaking or deforming. The solid disc design, crude as it seems, actually worked well for this purpose. The continuous wood structure distributed forces effectively, much better than a hollow wheel would. As carts became more sophisticated, axle technology evolved rapidly. One crucial innovation was the invention of axle caps protective coverings. Over the axle ends, but kept dirt and debris out of the bearing surfaces. Another was the development of grease boxes, reservoirs of lubricant that slowly fed grease into the bearing. These seem like minor improvements, but they dramatically extended axle life and reduced maintenance. Different civilizations developed variations on the basic axle design. In some regions, wheelwrights began using bronze or copper sleeves in the wheel hubs, creating harder, smoother bearing surfaces. The Egyptians, in their chariot construction around 2000 BCE, pioneered leather washers and complex multi-piece axle systems that allowed wheels to be easily removed for replacement or repair. The mathematical understanding required for effective axle design is surprisingly sophisticated. The axle must be strong enough to support the load without bending, which requires understanding beam strength and deflection. The wheel must be strong enough to handle the forces transmitted through it, which requires understanding compression and stress distribution. The bearing surfaces must be large enough to distribute the load without excessive wear, which requires understanding pressure and friction. Of course, ancient Sumerian engineers didn't have the mathematical formalism we use today. They couldn't calculate stress-strain relationships or coefficient of friction. But through empirical observation and trial and error, they developed intuitive understanding of these principles. They knew that thicker axles were stronger. They knew that larger bearing surfaces wore better. They knew that lubricants reduced friction and that harder materials wore less than softer ones. This empirical knowledge was transmitted through apprenticeship and practice. Master wheelwrights trained apprentices, teaching them not just the techniques, but the principles. Make the axle from oak, not pine. It's stronger. Smooth the bearing surface as much as possible. Rough surfaces wear faster. Apply fat regularly. It makes the wheels turn easier. This traditional knowledge accumulated over generations, gradually refining the technology. The axle seems so simple in retrospect. It's just a stick connecting two wheels. But that simple stick had to be precisely the right length, diameter, straightness, and surface finish. It had to be mounted at exactly the right height on the cart. The wheels attached to it had to be identical in size and precisely aligned. The entire system had to be maintained regularly, re-lubricated, adjusted as wear occurred. The genius of the axle is that it solved a problem that isn't obvious until you tried to build a cart. Early humans could imagine wheels. They could even make wheels. But making wheels actually work as transport required understanding the complex relationship between rotation, friction, load distribution, and structural mechanics. The axle was where all these factors came together, where theory met practice, where imagination became engineering. Every time a Sumerian cart rolled across the Mesopotamian plain, it was a testament to human ingenuity. Not just the simple ingenuity of making a circle, but the sophisticated ingenuity of making that circle rotate smoothly under heavy loads over long distances. The wheel gets the glory, but the axle did the work. And in those carefully crafted wooden beams connecting wheel to cart, we see humanity learning to think like engineers, to solve complex problems through systematic innovation, to build technologies that would carry us, literally and figuratively, into the future. Chapter 4. Solid Wheels and Heavy Dreams. The first transportation wheels weren't elegant. They were heavy, cumbersome things, solid discs of wood that weighed as much as the cargo they carried. A typical Sumerian cartwheel from 3000 BCE, measuring about 80 centimeters in diameter and 5 centimeters thick, weighed approximately 40 to 50 kilograms. A pair of wheels alone could weigh 100 kilograms before you added the cart frame, the axle, or any cargo. And yet, for more than 1,000 years, this was the cutting edge of transportation technology. Why start with solid wheels? The answer is simple. They were the easiest to make with available tools and the strongest for their size. Creating a hollow or spoked wheel requires sophisticated carpentry, precise measurements, and an understanding of stress distribution. A solid disc just requires cutting a circle from wood, difficult enough with Bronze Age tools, but conceptually straightforward. The construction process for solid wheels was labor-intensive but achievable. Wheelwrights would select suitable timber, usually oak, ash, or similar hardwoods known for strength and durability. They couldn't simply slice a disc from a tree trunk. Wood cut this way, across the grain, splits easily and lacks structural integrity. Instead, they cut planks along the grain and joined them. The typical construction method involved 3 planks. The center plank, running lengthwise, would be perhaps 20 to 30 centimeters wide. 2 side planks, each slightly wider, flanked it. Wooden crosspieces, shaped like thick dowels, were driven through holes drilled across all 3 planks, binding them together. This created a rectangular assembly that was then shaped into a circle. Shaping the circle was the most challenging part. With only copper or early bronze tools, axes, adzes, chisels, the wheelwright would carefully cut away excess wood, rotating the assembly and cutting symmetrically to approximate a circular shape. The work required enormous skill. Cut too much, and you weakened the wheel. Cut unevenly, and it would wobble. The final smoothing and truing of the circle might take days of patient work. The center hole for the axle was equally critical. Drill it even slightly off-center, and the wheel would have a pronounced wobble, rapidly destroying itself and the axle through uneven forces and vibration. Drilling a clean, perfectly centered hole through thick wood with primitive tools was extremely difficult. The wheelwright would likely mark the center carefully using geometric methods, perhaps crossing diagonals from the circle's edge, then drill from both sides to meet in the middle, hoping the holes aligned properly. Once completed, solid wheels had significant advantages beyond just being relatively simple to construct. Their continuous wood structure was remarkably strong. Forces distributed evenly through the disc, with no weak points. Unlike spoked wheels, which could fail if a single spoke broke, solid wheels remained functional, even with cracks or damage. They could handle rough terrain, heavy impacts, and substantial loads without catastrophic failure. But the disadvantages were equally significant. Weight was the most obvious problem. Those 100 kilograms of wheel weight represented wasted effort energy spent moving the wheels themselves rather than the cargo. The weight also meant that substantial force was needed to accelerate or decelerate the cart. Starting from a standstill required overcoming the inertia of not just the cargo, but also these massive wheels. The rotational inertia compounded the problem. A heavy wheel not only resists linear acceleration, but also resists rotational acceleration. Getting solid wheels spinning required significant effort, and once spinning, they wanted to keep spinning, making stopping equally difficult. This is why early carts were pulled by strong draft animals, like oxen rather than humans. The force required was simply too great for human power alone. Maneuverability suffered too. Turning a cart with solid wheels required either that the wheels slip sideways, creating enormous friction and making tight turns nearly impossible, or that the 2 wheels rotate at different speeds. Early fixed axle designs, where both wheels and axle rotated as one unit, made turning particularly difficult. The inside wheel wanted to rotate slower than the outside wheel, but being rigidly connected to the axle, it couldn't. The result was that one wheel had to skid, creating drag and rapid wear. Terrain limitations were another major constraint. Solid wooden wheels, despite their strength, had poor traction on soft ground and could sink into mud or sand. The flat bottom contact created significant rolling resistance. The wheels worked best on firm, relatively level ground, which meant that early wheeled transport was largely limited to roads or well-packed paths. Despite these limitations, solid wheels spread across the ancient world wherever wheeled transport was adopted. From Mesopotamia to Egypt, from the Indus Valley to Eastern Europe, archaeological finds from 3000 to 2000 BCE show remarkably similar solid wheel construction. This consistency suggests that the basic design represented an optimized solution given available materials and technology. Regional variations emerged based on available resources and specific needs. In areas with different tree species, wheelwrights adapted their techniques. Some regions developed wheels from single pieces of wood where very large trees were available, though this remained rare due to the difficulty of working across the grain. Others experimented with more complex joinery, using wedges or pegs instead of crosspieces to bind the planks. The weight problem of solid wheels created demand for innovation, but solving it wasn't straightforward. Simply making wheels thinner weakened them too much. They'd split under load. Cutting holes in the disc likewise created weak points. The solution would require rethinking the wheel structure entirely, moving from a solid disc to a framework design. But that innovation was still centuries away. In the meantime, solid wheels served their purpose. They enabled the first long-distance trade networks, carrying goods from city to city. They supported the first large-scale construction projects, transporting stone and timber. They revolutionized agriculture, moving harvests from fields to storage. They even began to change warfare, as the first primitive war wagons appeared around 2500 BCE. The solid wheel represents a crucial phase in technological evolution, the proof of concept phase. It demonstrated that wheeled transport worked, that the investment in creating carts and the infrastructure they required, roads, bridges, storage facilities, was worthwhile. It created markets for wheeled vehicles and the craftspeople who made them. It established wheels as essential technology rather than experimental novelty. And perhaps most importantly, solid wheels revealed their own limitations so clearly that they drove the next wave of innovation. Every time a cart maker struggled to lift a massive solid wheel, every time draft animals strained to pull heavy carts up an incline, every time a wheel cracked from stress or wore out from friction, the limitations of the solid design became obvious. These weren't merely inconveniences. They were constraints that limited what wheeled transport could accomplish. The solid wheel, heavy and cumbersome as it was, carried civilization forward, literally, for over a millennium. It transported the goods that built cities, the food that fed armies, the materials that enabled monumental architecture. It was a heavy dream made real, a circular piece of wood that proved humans could harness rotation for transportation. And in doing so, it set the stage for the innovation that would finally make wheels truly soar. The spoked wheel, which would reduce weight while maintaining strength, and in the process, change the world yet again. Chapter 5. The Spoked Revolution around 2000 BCE. Somewhere on the Eurasian steppe, a wheelwright looked at a solid wooden wheel and asked a question that would change warfare, trade, and transportation forever. What if we don't need all this wood? The spoked wheel represents one of the most elegant engineering solutions in human history. Instead of a solid disc of wood carrying loads through compression across its entire structure, imagine a wheel as a framework, a rim connected to a hub by thin spokes radiating outward like the sun's rays. Each spoke is a slender beam under tension and compression, and together they support the same loads as a solid disc while using perhaps 1/10 of the material. The genius is in the geometry. A typical Bronze Age spoked wheel had 4 to 8 spokes arranged symmetrically around the hub. When weight pressed down on the hub, it transmitted forces outward through the upper spokes to the rim. The rim, being circular, distributed these forces around its circumference until they concentrated at the ground contact point. The lower spokes, pressed between the hub and ground, carried the weight in compression like pillars. Meanwhile, the upper spokes pulled inward, holding the hub centered and preventing the rim from collapsing. This distribution of forces meant that each component could be surprisingly slender. A spoke might be only 3 to 4 centimeters in diameter, thin enough that an adult could encircle it with one hand, yet strong enough to support hundreds of kilograms when working as part of the complete wheel. The weight savings were dramatic. Where a solid wheel might weigh 50 kilograms, a spoked wheel of the same diameter weighed perhaps 8 to 12 kilograms. A pair of spoked wheels reduced cart weight by 80 kilograms or more. But creating spoked wheels required engineering sophistication far beyond solid wheel construction. Every component had to be precisely crafted and carefully joined. The hub needed a central hole for the axle, and precise holes or slots arranged symmetrically around its circumference to receive the spokes. Getting these holes positioned accurately was critical. Even small asymmetries would create unbalanced forces that could tear the wheel apart. The spokes themselves had to be shaped from strong, straight-grained wood. Each spoke was typically carved to be thicker at the ends and slightly thinner in the middle, maximizing strength where forces concentrated while minimizing weight. The ends were shaped to fit tightly into the hub and rim sockets. Any looseness would allow movement, and movement under load meant rapid wear and eventual failure. The rim presented its own challenges. It had to be circular, strong enough to resist the inward pull of the spokes without deforming, and properly socketed to receive the spoke ends. Early rims were made by bending thin planks of wood into circles, a technique requiring soaking or steaming the wood to make it pliable, then clamping it into shape while it dried. Later wheelwrights developed techniques for joining multiple curved segments to create the circular rim. Assembly required exceptional craftsmanship. The spokes had to be driven into their sockets tightly enough to prevent movement but without splitting the hub or rim. The tension had to be balanced. If one spoke was tighter than the others, it would distort the wheel shape. Some wheel makers used wedges driven into the spoke sockets to tighten the fit. Others relied on precise dimensional control, making spoke ends that fit so tightly they could barely be driven into place. The most advanced Bronze Age spoked wheels featured metal reinforcement. Around 1500 BCE, wheelwrights began adding bronze or iron bands around the rim, the first tires. These metal bands protected the wood from wear and splitting, dramatically extending wheel life. They also added rigidity to the rim, allowing thinner, lighter wooden construction. Fitting these metal tires required sophisticated techniques. The metal band was made slightly smaller than the wooden rim, heated to expand it, dropped over the rim, and allowed to cool and contract, creating a tight, permanent fit. The spoked wheel's impact was most dramatic in warfare. The chariot, enabled by spoked wheels, revolutionized Bronze Age combat. Solid-wheeled war wagons had existed since about 2500 BCE, but they were slow, cumbersome vehicles requiring 4 draft animals and carrying crews of 4 or more soldiers. They were mobile fighting platforms but lacked speed and maneuverability. The spoked-wheel chariot changed everything. With wheels weighing 1/5 as much, chariots could be pulled by just 2 horses and achieve unprecedented speeds, perhaps 30 to 40 kilometers per hour, faster than any human could run. The lighter construction allowed for single-horse or 2-horse teams, making chariots nimble enough for battlefield maneuvers. A skilled charioteer could wheel about, charge, retreat, and flank enemy formations with a mobility previously impossible. The chariot became the dominant military technology from approximately 1700 to 1200 BCE across the Middle East, Egypt, and parts of Europe and Asia. Armies were measured by their chariot strength. Egypt under Ramesses II deployed perhaps 2,500 chariots at the Battle of Kadesh. The Hittites, masters of chariot warfare, developed sophisticated tactics using chariot squadrons as shock troops, breaking enemy formations before infantry moved in. The social impact of chariots was equally profound. Owning and operating a chariot required wealth. The vehicle itself was expensive, requiring skilled craftsmen weeks to construct. The horses required feeding and training. The charioteer needed extensive practice to master the difficult skill of controlling a team at high speed while managing weapons. This created a chariot-owning aristocracy across Bronze Age civilizations, a warrior elite whose military importance translated into political power. Beyond warfare, spoked wheels revolutionized trade and communication. Lighter carts could travel faster and farther, reducing journey times and expanding trade networks. The same weight of cargo could be transported with fewer draft animals, reducing costs. Roads became more important. The faster vehicles could travel, the more valuable good road infrastructure became. Archaeological evidence shows increased road construction across the ancient world, coinciding with the spread of spoked wheels. The technological knowledge required to build spoked wheels didn't spread uniformly. It appears to have originated in the Eurasian steppes, possibly among Indo-European peoples like the Stintashta culture around 2000 BCE. From there, it spread rapidly into Mesopotamia, Anatolia, Egypt, and eventually Europe and China. But the spread wasn't passive. It required transferring sophisticated craftsmanship, not just conceptual knowledge. A craftsman who debuilt solid wheels their entire life couldn't simply start making spoked wheels without training. The techniques were fundamentally different, requiring new tools, new skills, new understanding of materials and joinery. This meant that spoked wheel technology spread through migration of skilled craftsmen, through trade in finished wheels, and through deliberate technology transfer as societies recognized the military and economic advantages and sought to acquire the capability. China provides a fascinating case study. Spoked wheels appeared around 1200 BCE, clearly influenced by Western technologies brought along early Silk Road trade routes. But Chinese wheelwrights didn't simply copy Western designs. They adapted them, eventually developing wheels with 18 to 28 spokes, far more than typical Western wheels. These many-spoked wheels distributed forces differently, allowing for a lighter construction while maintaining strength. Chinese chariots became renowned for their quality, eventually influencing Central Asian designs in return. The spoked wheel's triumph wasn't absolute or immediate. Solid wheels continued to be used for heavy freight wagons long after spoked wheels became standard for chariots and lighter vehicles. The reason was practical spoked wheels, while lighter, were more delicate. They could break if overloaded or subjected to severe impacts. For hauling stone, timber, or other very heavy loads, solid wheels' ruggedness remained advantageous. Even into the Iron Age, we see both technologies coexisting, each optimized for different applications. The engineering principles underlying spoked wheels anticipated later structural innovations. The concept of using slender members under tension and compression rather than solid masses appears in countless later technologies, from bridges, using cables and trusses to modern bicycle wheels with their thin wire spokes. The same geometric principles that made spoked wheels work would be rediscovered and refined over millennia. Yet for all their sophistication, Bronze Age spoked wheels still had limitations. The wooden construction, even with metal reinforcement, wore rapidly. Spokes could break, rims could crack, hubs could split. A chariot in active military service might need wheel replacement or major repairs after just months of use. This constant maintenance requirement created entire industries of wheelwrights, metallsmiths, and timber suppliers supporting Bronze Age armies. The spoked wheel revolution demonstrates how innovation builds on innovation. Potter's wheels led to solid transport wheels, which revealed their limitations, driving innovation toward spoke designs. Each stage required not just new ideas but new materials, new tools, and new skills. The spoked wheel couldn't have been invented without bronze tools for precise carpentry and bronze or iron for rim reinforcement. It needed horses, domesticated and bred for strength and speed, to justify the lighter construction. It needed societies wealthy and complex enough to support specialized craftsmen creating sophisticated products. This is why the spoked wheel appeared when it did, where it did. not because earlier peoples were less intelligent or capable, but because the entire technological and social ecosystem needed to evolve first. The Sumerians, who invented the potter's wheel and solid transport wheels, were just as clever as the steppe peoples, who later invented spoked wheels. But they lived in different times, with different tools, different animals, different needs. Innovation isn't just about individual genius. It's about the intersection of need, capability, and context. The spoked wheel rolled across the ancient world, light and strong, transforming everything it touched. It made fast chariots possible, changing warfare. It made long-distance trade practical, changing commerce. It created new industries and new social classes. And it demonstrated that the simplest ideas, a framework instead of a solid mass, could have revolutionary consequences. The revolution had begun with clay spinning on a disc, and now it accelerated, wheels turning faster, carrying civilization forward into an age of bronze, chariots, and roads that connected empires. Chapter 6. Chariots of War and Glory. Dawn breaks over the battlefield at Kadesh, Syria, 1274 BCE. The air fills with the thunder of hooves and the rumble of wheels on packed earth. Ramesses II of Egypt commands 2,500 chariots, each carrying a driver and an archer, racing across the plain in clouds of dust. The Hittite forces counter with their own chariot corps, heavier vehicles carrying 3 men: driver, archer, and shield-bearer. The fate of empires hangs on how well these wheels turn, how fast these horses run, how effectively these mobile platforms deliver death from a distance. The chariot wasn't just a military innovation. It was a revolution that redefined warfare for nearly 1,000 years. Before chariots, armies moved at walking pace, limited by the speed of marching infantry. Battles were largely decided by hand-to-hand combat between massed formations. The introduction of light, fast, spoked-wheel chariots changed everything, introducing speed, mobility, and ranged combat that infantry couldn't match. The earliest chariots, emerging around 2000 BCE, were miracles of Bronze Age engineering. The chassis was deliberately lightweight, often made from bent wood frames that combined flexibility with strength. Egyptian chariots, some of the finest ever built, weighed as little as 34 kilograms without horses or crew light enough for 2 men to carry. This lightweight construction meant that 2 horses could pull the vehicle at considerable speed while still having energy to maneuver in battle. The design centered on the wheels, typically 1 meter in diameter with 4 or 6 spokes. The axle placement was crucial. Egyptian chariots mounted the axle at the rear of the chassis, which made them more stable at high speed and absorbed shocks better, crucial for maintaining the archer's aim. Hittite chariots often placed the axle centrally, sacrificing some high-speed stability for better maneuverability and easier turning. The crew stood on a small platform, often woven from leather strips for flexibility that absorbed vibrations. The driver, holding reins connected to bits in the horses' mouths, needed exceptional skill. Controlling a team of horses at full gallop while navigating rough terrain and avoiding obstacles required years of training. The slightest mistake, a stumbled horse, a broken rein, a lost wheel, could send the chariot tumbling, killing or injuring the crew. The archer was the primary weapon system. Armed with a composite bow, a sophisticated weapon made from wood, horn, and sinew laminated together, a skilled chariot archer could fire arrows with devastating accuracy while moving at speed. The effective range was perhaps 100 meters, but the real advantage was mobility. Chariot archers could approach infantry formations, unleash volleys of arrows, and retreat before the foot soldiers could respond. They could flank enemy positions, pursue fleeing troops, or harass supply lines. Chariot warfare developed sophisticated tactics. Squadrons of chariots would operate in coordination, much like later cavalry formations. They'd execute flanking maneuvers, encirclement, feigned retreats, and concentrated charges. Commanders learned to combine chariots with infantry. Chariots would soften enemy formations with arrow fire. Then infantry would close for hand-to-hand combat. Against other chariots, engagements became high-speed chases and archery duels. The social structure of Bronze Age armies revolved around chariots. A chariot crew represented significant investment. The vehicle itself cost as much as several houses. The horses required years of breeding and training, and the crew needed extensive practice. Only the wealthy could afford chariots, creating a chariot-owning aristocracy that dominated military and political power. In Egypt, chariot warriors formed an elite class. In Mesopotamia, the Marianu warriors were professional charioteers who formed the military backbone of kingdoms. Training a chariot crew took years. The driver had to learn not just to control horses, but to do so in combat conditions amid noise, chaos, enemy action. The archer had to master shooting from a moving, bouncing platform, compensating for speed and direction. The crew had to work as a seamless team, the driver positioning the chariot while the archer focused on targets. Mock battles and hunting expeditions served as training grounds, building skills and coordination. The infrastructure supporting chariot warfare was extensive. Breeding programs produced horses strong enough to pull chariots, yet fast enough for battlefield maneuvers. Stables, training grounds, and pastures had to be maintained. Workshops employed specialized craftsmen, wheelwrights, carpenters, leather workers, metal workers, producing chariots and maintaining them. A single chariot might require replacement wheels every few months of active campaigning. Broken axles, cracked chassis, worn harnesses. The maintenance burden was enormous. The spread of chariot warfare reshaped geopolitics. Kingdoms that mastered the technology gained decisive military advantages, conquering neighbors who hadn't. The Hittites used chariots to build an empire across Anatolia. The Egyptians, under the New Kingdom, employed chariots to extend control into Syria and Nubia. In China, the Shang dynasty's military power rested on chariot forces. The technology forced other societies to adapt or be overwhelmed. But chariots had limitations that eventually led to their decline. They required relatively flat, open terrain. Forests, mountains, and broken ground made them useless. They were expensive to build and maintain, limiting army sizes. The crew was vulnerable to concentrated arrow fire or disciplined infantry armed with long spears. And most crucially, they depended on maintaining speed and mobility. If chariots got bogged down or surrounded, they became death traps rather than assets. The development of effective cavalry warriors, fighting from horseback rather than from chariots, began to displace chariots from battlefields around 1000 BCE. Mounted warriors were more flexible, required less infrastructure, and could fight in terrain unsuitable for chariots. Improvements in horse breeding produced animals strong enough to carry armored riders. New developments in riding equipment, better saddles, eventually stirrups made cavalry increasingly effective. Yet chariots didn't disappear immediately. They remained symbols of power and prestige long after their military effectiveness declined. Kings rode in ornate chariots during ceremonies. Chariot racing became immensely popular in Greek, Roman, and Byzantine civilizations. The Circus Maximus in Rome could hold 250,000 spectators watching chariot races. The chariots used in these races were even lighter and faster than war chariots, designed for pure speed rather than combat utility. The legacy of war chariots extended beyond their military role. They drove technological innovation in metallurgy, woodworking, and animal husbandry. The demand for lighter, stronger wheels advanced engineering knowledge. The need for faster horses improved breeding programs. The tactical lessons learned in chariot warfare mobility, combined arms, coordination influenced military thinking for centuries. Archaeological discoveries continue revealing the sophistication of ancient chariots. In 1922, Howard Carter's excavation of Tutankhamun's tomb uncovered 6 complete chariots, providing unprecedented insight into Egyptian chariot construction. The craftsmanship was extraordinary: bent wood chassis using steam-bending techniques, precision joinery, decorative inlays of gold and precious materials. These weren't just weapons. They were works of art demonstrating the pinnacle of Bronze Age technology. In 2018, archaeologists in Italy discovered a ceremonial chariot at Pompeii, preserved by volcanic ash for nearly 2,000 years. Though this was a Roman chariot used for ceremonies rather than war, it demonstrated how chariot technology evolved and persisted. The iron-tired wheels, sophisticated suspension, and ornate decorations showed centuries of accumulated improvements since the first Bronze Age war chariots. The chariot story is ultimately about how a simple invention, the wheel, enabled something far more complex. Spoked wheels made light, fast chariots possible. Those chariots changed warfare. Changed societies, creating new power structures, new tactical thinking, new industries. The wheels that turned under those chariots literally drove historical change, carrying warriors into battle and civilizations into new eras. Today, no one rides chariots into battle, but their influence echoes through history. The roads built to accommodate chariot traffic became the foundations of trade networks. The tactical principles developed in chariot warfare influenced cavalry tactics and eventually armored warfare. The social structures created by chariot-owning aristocracies shaped political development across civilizations. And the engineering knowledge gained building light, strong, fast chariots contributed to countless later innovations. The chariots of war and glory are gone, but the wheels keep turning, carrying their lessons forward through time. Chapter 7: The Wheel That Fed Civilizations. While chariots dominated battlefields and captured imaginations, a quieter revolution was transforming agriculture across the ancient world. The wheel that fed civilizations wasn't dramatic or glorious. It was practical, patient, and productive. It turned in fields, beside irrigation canals, and in grain mills, making possible the food surpluses that supported cities, armies, and everything we call civilization. The wheeled plow, appearing around 3000 BC in Mesopotamia, represents one of agriculture's most important innovations. Before wheels, plows were simple wooden implements dragged through soil, scratching shallow furrows. They worked, but barely, and required multiple passes to prepare fields adequately. The addition of wheels changed everything. A wheeled plow mounted the plowshare, the cutting blade on a frame supported by 2 wheels. This arrangement allowed much deeper cutting because the wheels, not the ground, supported the plow's weight. The depth could be controlled by adjusting the wheel height. The design also reduced friction dramatically. Instead of the entire plow dragging through dirt, only the cutting edge engaged the soil while the wheels rolled smoothly over the surface. The impact on productivity was enormous. A farmer with a wheeled plow could perhaps 3 times as much land in a day as with an old-style plow. The deeper cutting meant better soil preparation, improved drainage, and more effective weed control. Fields could be worked more thoroughly with less labor, freeing agricultural workers for other tasks or allowing smaller populations to work larger areas. The spread of wheeled plows paralleled the spread of wheeled transport. Regions that adopted carts and wagons soon developed wheeled plows. The technology transferred easily. Wheelwrights, who made transport wheels, could make plow wheels. Draft animals already used for pulling carts could pull plows. The infrastructure of roads and workshops supported both applications. But the agricultural wheel's most transformative application was in irrigation. Ancient Mesopotamia's civilization depended on managing water from the Tigris and Euphrates rivers. During seasonal floods, water was abundant, sometimes devastatingly so. During dry seasons, fields needed irrigation or crops would fail. Moving water from rivers to fields was labor-intensive and limiting. The water wheel, developed around 3000 BCE, mechanized this crucial task. Early designs were simple but ingenious. A large wheel, perhaps 3 to 4 meters in diameter, was mounted horizontally beside a river or canal. Around the wheel's rim, workers attached clay pots or wooden buckets. The river's current rotated the wheel. As buckets on the lower side dipped into the water and filled, the wheel's rotation lifted them to the top, where they emptied into a trough that channeled water to irrigation canals. This device, sometimes called a noria, required no power beyond the river's natural flow. Once built, it worked continuously, day and night, as long as water flowed. A single water wheel could irrigate fields that would otherwise require dozens of workers hauling water. The productivity gain was staggering, and the impact on agricultural output was revolutionary. More sophisticated water-lifting wheels appeared over time. The Zakia, developed perhaps around 300 BCE, used animal power. A vertical wheel, turned by an ox or donkey walking in a circle, drove gears that rotated a horizontal wheel mounted with buckets. This design could lift water from deep wells or raise it to heights impossible for river-powered wheels. The mechanical advantage of gears, another application of rotary motion, multiplied the animal's strength, allowing water to be lifted that would have been impossible to raise manually. The grain mill represents another crucial agricultural application of wheels. Grinding grain processing wheat, barley, or other cereals into flour was essential for bread-based diets, but incredibly labor-intensive. Traditional methods used hand-operated querns, grinding stones, which required enormous effort and could process only small quantities. The rotary quern, emerging around 500 BCE, was essentially a wheel applied to milling. Two circular stones were mounted one atop the other. Grain poured through a central hole in the upper stone fell between the stones. As the upper stone rotated, the grain was ground between the stones, emerging as flour at the edges. A single person turning the upper stone by hand could grind far more efficiently than with traditional methods. Water-powered grain mills, appearing around 1st century BCE, took this further. A water wheel, turned by a stream's current, drove gears connected to the millstone. No human effort was required. The mill operated continuously as long as water flowed. A single water mill could produce enough flour for an entire village, freeing enormous amounts of labor for other purposes. These agricultural applications of wheels shared common principles. They converted linear or flowing motion into rotary motion, or used rotary motion to accomplish tasks more efficiently than linear methods. They mechanized tasks that had previously required constant human labor. They allowed nature's forces, water flow, animal strength, to do work that humans had done manually. The social and economic impacts extended far beyond agriculture. Water wheels and grain mills required capital investment and technical knowledge, creating new classes of mill operators and irrigation specialists. Control of water wheels meant control of irrigation, giving power to those who owned or managed them. Mill ownership became a source of wealth and influence. The freed labor had profound effects. When fewer farmers could produce more food, populations could support larger numbers of craftspeople, soldiers, administrators, and priests. Cities could grow larger because their agricultural hinterlands produced greater surpluses. Armies could campaign longer because logistics improved. Civilization became more complex because the economic foundation food production became more productive. Regional variations in wheel-based agriculture developed based on local conditions. In areas with strong rivers, water wheels dominated. In flatter regions with less reliable water flow, animal-powered wheels were more common. In mountainous areas with limited suitable locations for water wheels, traditional methods persisted longer. Egypt provides a striking example of selective wheel adoption. Egyptians were relatively late to adopt wheeled transport for freight, preferring to use Nile boats for moving goods. But they embraced water wheels enthusiastically, using them extensively for irrigation. The Nile's reliable annual flooding made water lifting crucial during dry seasons, and water wheels addressed the need perfectly. China developed unique wheel-based irrigation technologies. The square pallet chain pump, invented around 1st century CE, used a wheel to drive an endless chain of wooden pallets up an inclined trough, lifting water continuously. Multiple wheels could be linked in series to lift water substantial heights. These devices became ubiquitous in Chinese agriculture, symbols of the civilization's engineering sophistication. The Islamic Golden Age, 8th–13th century CE, saw remarkable advances in water wheel technology. Engineers designed massive wheels, some over 20 meters in diameter, capable of lifting water to impressive heights. The wheels at Hama, Syria, some still functioning today, are medieval engineering marvels. The knowledge and techniques developed in this era spread through Islamic territories and eventually influenced European mill design. Medieval Europe saw explosive growth in watermill usage. By 1086 CE, the Domesday Book recorded over 6,000 watermills in England alone, approximately 1 mill for every 350 people. Mills ground grain, powered bellows for forges, drove saws for lumber, processed cloth wheels turned for countless purposes, all deriving from that original Mesopotamian insight that rotary motion could accomplish what linear motion couldn't. The wheel that fed civilizations didn't race across battlefields or carry kings in triumph. It turned slowly in fields and beside rivers, patient and persistent. But its impact was deeper and more lasting than any chariots. Without the agricultural productivity that wheels enabled, cities couldn't have grown, armies couldn't have been fed, and civilization as we know it couldn't have developed. The glory went to war chariots, but the real work was done by wheels lifting water, grinding grain, and breaking earth. Turning, feeding the world. Chapter 8. When cultures adopted the circle, the wheel didn't spread like a virus, infecting every culture it contacted. Its adoption was selective, strategic, and often surprisingly slow. Understanding why different civilizations embraced or rejected wheel technology reveals how innovation depends not just on knowledge, but on context, need, and infrastructure. The story of the wheel spread is really multiple stories. Egypt's delayed adoption, China's enthusiastic embrace, the Indus Valley's parallel development, and Europe's gradual acceptance. Egypt presents one of history's most puzzling wheel stories. The Egyptians had extensive contact with wheel-using Mesopotamian civilizations from at least 3000 BCE. They knew about wheels. Archaeological evidence shows wheeled vehicles in Egypt by 2000 BCE, probably introduced through trade contacts or military encounters. Yet for freight transport, Egyptians continued relying heavily on boats and sledges long after wheels became standard elsewhere. Why? The Nile. Egypt's geography centered on a single great river flowing north, with prevailing winds blowing south. Boats could sail upstream using wind power and float downstream with the current. This created a transportation system more efficient than early wheeled carts, particularly for heavy loads. The Nile Valley's narrow, cultivated strip meant that most goods were destined for river ports anyway. Roads were less necessary when the river served as a highway. Where Egyptians did embrace wheels was in warfare and ceremony. The chariot arrived in Egypt around 1650 BC, introduced by the Hyksos invaders who conquered Lower Egypt. The Egyptians, impressed and alarmed by this technology's military effectiveness, didn't just adopt it, they perfected it. Egyptian chariots became the finest in the ancient world, lighter and faster than any contemporary design. The Egyptian chariot building industry demonstrates how selective adoption works. Once Egyptians recognized chariots' military value, they committed fully, developing specialized workshops, training programs, and supply chains. They imported wood from Lebanon because local timber wasn't suitable. They bred horses specifically for chariot warfare. They created an elite chariot corps that became the Egyptian army's striking force. When wheels served a critical need, Egypt didn't just adopt the technology, they mastered it. China's wheel adoption followed a different pattern. Spoked wheels appeared around 1200 BCE, clearly diffused from Western cultures along early trade routes. But Chinese wheelwrights didn't passively copy Western designs. They experimented, innovated, and eventually developed distinctive Chinese wheel forms. Chinese chariot wheels often featured 18 to 28 spokes compared to the 4 to 8 typical of Western designs. This wasn't mere decoration. The additional spokes distributed forces differently, allowing for lighter, more flexible construction. Chinese chariots developed curved poles and double shafts that reduced strain on horses and improved maneuverability. These innovations eventually influenced Central Asian designs, showing that technology transfer wasn't one-directional. China also developed unique wheel devices for other purposes. The wheelbarrow, invented around 100 BCE in China, didn't appear in Europe for another 1,000 years. Chinese wheelbarrows featured a large central wheel supporting the load directly, allowing a single person to transport substantial weights. This design was more efficient than European wheelbarrows, which positioned the wheel at the front, requiring the operator to carry part of the load. The Indus Valley civilization presents an intriguing case of possible independent wheel invention. Wheeled toys dating to around 2000 BCE have been found at multiple Indus sites. Whether these represent independent invention or diffusion from Mesopotamia remains debated. The geographic proximity and evidence of trade contacts suggest diffusion is more likely, but the rapidity with which wheels appeared and the distinctive local designs indicate that Indus peoples quickly made the technology their own. Europe's wheel adoption was gradual and uneven. The Ljubljana Marshes wheel from Slovenia, dated to around 3150 BCE, shows that wheels reached Europe relatively early. But adoption wasn't uniform. Archaeological evidence suggests wheels spread first to areas with trade contacts to wheel-using civilizations, then gradually inland. Geography mattered. Regions with navigable rivers sometimes showed slower wheel adoption, similar to Egypt. Because water transport remained competitive, the Celtic peoples of Iron Age Europe became renowned wheelwrights, developing distinctive designs and introducing innovations like iron-rimmed wheels around 1000 BCE. Celtic wheels featured sophisticated joinery and sometimes included suspension systems, leather straps, or metal springs that absorbed shocks. These improvements made wheeled vehicles comfortable enough for long-distance travel, not just cargo transport. Contrast these adoption stories with civilizations that knew of wheels, but didn't adopt them for transportation. The most dramatic examples come from the Americas. Pre-Columbian civilizations, Maya, Aztec, Inca created sophisticated states with monumental architecture, complex agriculture, and extensive road networks. They knew about wheels. Archaeologists have found wheeled toys in Mexican sites dating to 100 to 800 CE, yet they never used wheels for transportation. The explanation isn't ignorance or lack of innovation. It's context. The Americas lacked suitable draft animals. Horses went extinct in the Americas around 10,000 BCE and weren't reintroduced until European colonization. Llamas, used in South American highlands, are too small to pull heavy carts and work well only as pack animals. Without draft animals, wheeled transport offers little advantage over human porters. Geography also mattered. Incan roads crossed steep Andean mountains where wheeled vehicles would be impractical. Mayan territories featured dense jungle and swampland unsuitable for carts. The terrain that these civilizations inhabited made wheels less advantageous than they were in the relatively flat regions where wheels first emerged. Additionally, these societies had effective alternatives. Mayan and Aztec cities featured extensive canal systems. Boats moved goods more efficiently than carts in these waterlogged environments. Incan civilization developed sophisticated porter systems and relay networks that moved goods across their empire effectively. Human labor was abundant, and porters could travel terrain impassable to carts. The American case illustrates a crucial principle. Technology adoption depends on cost-benefit analysis. Wheels aren't universally advantageous. They require infrastructure, roads, suitable terrain, relatively flat ground, and either draft animals or human labor. In contexts where boats, pack animals, or porters work better, wheels offer no advantage and may perform worse. Sub-Saharan Africa shows similar patterns. Wheeled transport remained rare until colonial times, not from ignorance but from context. Tsetse flies, which transmit diseases fatal to horses and cattle, made draft animals unsuitable in many regions. Dense forests and seasonal flooding created terrain unsuitable for carts. Human porters and later, camels served transportation needs adequately. The wheel spread, then, wasn't inevitable or universal. It was contextual. Civilizations adopted wheels when several conditions aligned: suitable terrain, available draft animals, need for land transport not met by alternatives, and technical capability to build and maintain vehicles. When these conditions existed, wheels spread rapidly. When they didn't, even knowledge of wheels didn't lead to adoption. This pattern continues today with all technologies. Innovation diffuses not simply based on availability, but on fit with existing infrastructure, cultural practices, and economic needs. The wheel's selective adoption across ancient civilizations teaches us that technology transfer is negotiated. Not automatic. Cultures assess innovations against their needs and contexts, adopting what works and ignoring what doesn't. The circle, for all its geometric perfection and mechanical elegance, only rolled where conditions allowed. And where it rolled, it transformed transportation, warfare, and agriculture. But where conditions didn't favor it, civilizations thrived without it, demonstrating that innovation's value is always contextual, always dependent on the intersection of technology, geography, economy, and need. Chapter 9. The cultures that rejected the wheel. Sometimes the most revealing question isn't why did they adopt this technology, but why didn't they? The civilizations that knew about wheels but chose not to use them for transportation aren't failures or anomalies. They're success stories that followed different paths. Understanding their choices illuminates how technology and culture interact, and why the best solution is always context-dependent. The Americas before European contact represent the largest and most dramatic case of wheel rejection. From the sophisticated Mayan city-states to the vast Incan Empire to the Aztec Confederation, American civilizations achieved remarkable complexity without wheeled transport. They built astronomical observatories, developed sophisticated mathematics, including the concept of zero, constructed massive pyramids in cities, created complex agricultural systems, all without a single cart rolling through their streets. The wheeled toys found in Mexican archaeological sites prove these societies understood the wheel principle. These artifacts, typically small clay animals mounted on axles with wheels, demonstrate that the concept of a wheel rotating on an axle was known. Some archaeologists argue these were children's toys. Others suggest religious or ceremonial purposes. Regardless, the knowledge existed. The choice not to apply it to transportation was deliberate, not ignorant. The absence of suitable draft animals was the primary practical constraint. The horses that once roamed the Americas went extinct around 10,000 years ago, likely from a combination of climate change and human hunting. Llamas and alpacas, domesticated in South America, are too small for pulling heavy loads. They work well as pack animals carrying perhaps 30 to 40 kilograms, but they can't pull carts effectively. Dogs, used by some North American peoples for pulling travois, are frame carriers, similarly lack the strength for heavy wheeled transport. Without draft animals, wheeled vehicles would need human power. Humans pulling carts can transport more than carrying by hand or on their backs, but the advantage is smaller than with animal power, especially on poor roads. When comparing a human pulling a cart to a human carrying a load, or two humans with a litter, the cart's advantage diminishes. Add the requirement for roads and the maintenance burden of wheels and axles, and wheeled transport often wasn't worth the investment. Geography compounded these challenges. The Incan Empire stretched along the Andes Mountains, featuring some of the world's most dramatic terrain: steep valleys, high passes, suspension bridges across gorges. Wheeled vehicles would be useless in most of this landscape. The magnificent Incan road network, including thousands of kilometers of stone-paved paths, was designed for human porters and llama trains, not carts. Steps, steep grades, and narrow paths made sense for foot traffic but would block wheels entirely. The Mayan lowlands presented different challenges, but equally unsuitable for wheels. Seasonal flooding, dense jungle, swampy terrain, and the famous sinkholes, cenotes, created landscapes where boats and footpaths worked better than roads for carts. The Mayans built causeways, raised stone roads, but these connected ceremonial centers and were designed for foot traffic, often too narrow for carts. Alternative technologies filled transportation needs effectively. Extensive canal systems in Aztec territory moved goods via canoe far more efficient than carts in a lake-filled landscape. The Incan Chasqui relay runner system communicated messages across the empire faster than carts could have traveled. Porter networks, organized through the Meta labor system, moved goods effectively throughout Incan territories. The economic context mattered too. Labor was relatively abundant in these agricultural societies, while capital for building and maintaining carts, roads suitable for wheels, and draft animals, even if available, represented significant investment. When comparing the cost of porter systems that worked well versus developing wheeled transport infrastructure that offered marginal benefits, the choice not to invest in wheels made economic sense. Sub-Saharan Africa provides another large-scale example of wheel rejection. Before colonial contact, wheeled transport was rare across most of the continent, limited mainly to North African regions with connections to Mediterranean and Middle Eastern wheel-using cultures. Yet African societies weren't isolated or technologically unsophisticated. Extensive trade networks crossed the continent. Kingdoms rose and fell. Ironworking and other technologies developed independently. The tsetse fly played a crucial role. These insects, prevalent across much of tropical Africa, transmit trypanosomiasis sleeping sickness in humans, nagana in cattle and horses. The disease is often fatal to livestock, making cattle and horses unreliable as draft animals in tsetse-infested regions. Camels, used extensively in the Sahara and Sahel regions, don't tolerate the humid tropical conditions farther south. Without reliable draft animals, wheeled transport offered few advantages. African terrain also presented challenges. Dense forests, seasonal flooding that made roads impassable for months, and the absence of stone suitable for paving in many regions made road infrastructure extremely difficult. Human porters, whose paths could navigate obstacles that would stop carts, remained more flexible and often more cost-effective. The monsoon regions of South and Southeast Asia show similar patterns. In areas with distinct wet and dry seasons, Roads that work during dry months become impassable mud during monsoons. Boats, capable of navigating flooded areas, often provided better year-round transportation than carts that would bog down during rainy seasons. Island societies, particularly in the Pacific, had obvious reasons for not emphasizing wheels. When your primary transportation challenge is crossing water between islands, boats matter far more than carts. The Polynesian peoples developed sophisticated maritime technologies, outrigger canoes, navigation techniques, double-hulled vessels that enabled migration and trade across vast ocean distances. Wheels would have been nearly useless for their needs. Even within Europe and Asia, wheel adoption wasn't universal. Some mountainous regions continued relying on pack animals long after wheels became standard in lowlands, simply because the terrain made carts impractical. Coastal regions with good harbors sometimes showed less investment in road infrastructure because maritime transport remained superior for bulk goods. These examples of wheel rejection teach us several important lessons. First, technological advancement is context-dependent. Wheels aren't universally superior. They're superior in specific contexts with suitable terrain, draft animals, and infrastructure. Second, knowing about a technology doesn't compel adoption. Societies make rational choices about which technologies to invest in based on cost-benefit analyses. Third, alternative technological paths can be equally effective porter systems. Boat networks and pack animal trains weren't primitive alternatives to wheels. They were sophisticated transportation systems, optimized for different conditions. The cultural dimension is equally important. Technologies don't exist in isolation. They're embedded in social structures, economic systems, and cultural practices. Adopting wheels meant more than just building carts. It meant reorganizing labor systems, investing in road infrastructure, developing wheelwright crafts, breeding or acquiring draft animals, and restructuring trade networks. For societies where existing systems worked well, this transformation represented disruption without clear benefit. Consider the Incan Empire's impressive organizational achievement. They managed communications and logistics across an empire stretching 2,500 miles, from Ecuador to Chile, without wheels. The chasqui runner system delivered messages faster than horse-drawn carts could have traveled the difficult terrain. The meta-labor system mobilized labor for road construction and maintenance, without requiring individual ownership of transport vehicles. State storehouses positioned along roads provided supplies for travelers and military forces. This was a sophisticated system that worked. When Europeans arrived with wheeled vehicles, they didn't immediately revolutionize transportation in many of these regions. The limitations that made wheels impractical for indigenous peoples' difficult terrain, lack of suitable animals, infrastructure requirements affected Europeans too. In many areas, traditional methods continued alongside or even outperformed European wheeled transport for decades or centuries. The Polynesian case is particularly instructive. These peoples developed navigation technologies that enabled intentional voyages across thousands of miles of open ocean, colonizing islands from Hawaii to Easter Island to New Zealand. This required sophisticated knowledge of astronomy, oceanography, boat design, and navigation techniques. By any measure, this represents technological sophistication equal to or exceeding that of contemporary wheel-using societies. Yet wheels would have been irrelevant to Polynesian needs and challenges. Modern technology adoption shows similar patterns. Developing nations don't always adopt the latest technologies from developed nations, even when aware of them. Instead, they adopt technologies that fit their context, sometimes leapfrogging intermediate stages entirely. Many African nations adopted mobile phones extensively, while landline infrastructure remained limited. Not because they didn't know about landlines, but because mobile technology, fit their needs and infrastructure better. Wheel rejection stories also reveal the danger of technological determinism, the assumption that better technology automatically displaces inferior technology. Technology adoption is negotiated through complex interactions of economics, culture, environment, and need. The best technology is always the best for a particular context, not universally best. This helps explain why the wheel, despite being one of history's most important inventions, wasn't universally adopted. It was crucial in the relatively flat, dry regions of Mesopotamia, Europe, and parts of Asia where draft animals were available and road construction feasible. It revolutionized transportation, warfare, and agriculture in those contexts. But in mountainous regions, dense forests, flooded lowlands, or areas without suitable animals, other technologies served better. The cultures that rejected wheels weren't backward or unimaginative. They were pragmatic, choosing technologies that worked for their circumstances. The Incas built an empire without wheels, but with sophisticated road networks, relay systems, and organizational structures. The Mayans developed complex astronomy and mathematics without applying wheels to transportation. Polynesians navigated the Pacific, using stars and currents without needing carts. This is perhaps the wheel's most important lesson. Innovation isn't about adopting every new technology, but about choosing the right tools for your context. The wheel was transformative where it fit. Elsewhere, different solutions work better, and choosing not to adopt wheels was as smart as adopting them was elsewhere. The cultures that rejected wheels didn't fail. They succeeded by different means, reminding us that there are many paths to achievement, many solutions to challenges, and many ways to build civilizations. Chapter 10. From wood to bronze to iron. The story of the wheel is also the story of materials. The same basic design, a circular object rotating on an axle, performed radically differently depending on what it was made from. The evolution from all-wood wheels to bronze-reinforced designs to iron-tired wheels parallels the broader development of human metallurgy, and each material advance transformed what wheels could do. The earliest wheels were entirely wooden by necessity. Before metals were common enough for structural use, wood was the obvious choice available, workable with existing tools and reasonably durable. But wood has significant limitations. It wears rapidly under friction, especially at bearing surfaces where wheel meets axle. It splits under stress, particularly along the grain. It swells when wet and shrinks when dry, causing joints to loosen. It's vulnerable to rot in damp conditions and insects in warm climates. Early wheelwrights learned to work with wood's properties rather than against them. They selected species carefully: oak for strength and durability, ash for flexibility and toughness, elm for its resistance to splitting. They oriented grain direction to maximize strength. They treated wood with oils or fats to resist moisture. They designed joints that allowed for seasonal expansion and contraction. This accumulated knowledge represented sophisticated material science, even without formal scientific understanding. The introduction of bronze around 3000 BCE opened new possibilities. Bronze, an alloy of copper and tin, was harder than pure copper, could be cast into complex shapes, and held an edge better than stone. Initially, bronze was too precious for structural use in wheels. Early Bronze Age wheels remained wooden, with bronze used only for small, critical components. The axle caps were among the first applications. These bronze sleeves protected wooden axle ends from wear and weather. They were relatively small, requiring minimal bronze, but significantly extended axle life. As bronze became more available, wheelwrights began using bronze bushings or sleeves inside wheel hubs. These harder metal surfaces were much better than wood-on-wood bearings, reducing friction and maintenance. Around 1500 BCE, Bronze rim reinforcement appeared on high-quality wheels, particularly chariot wheels. Bronze bands or strips were attached to wooden rims, protecting the wood from wear and impact damage. These bands added weight, but for lightweight chariot wheels where durability was crucial, the trade-off was worthwhile. The bronze could also be shaped with decorative patterns, making wheels symbols of wealth and status. The transition to iron changed everything. Iron, developed around 1200 BCE and becoming widespread by 1000 BCE, was harder and more durable than bronze, and crucially, iron ore was far more abundant than tin, making iron less expensive. The falling cost of metal made structural use practical rather than extravagant. Iron tire bands, fitted around wheel rims, became standard on quality wheels from about 800 BCE onward. The technique was remarkable in its simplicity and effectiveness. A band of iron was forged to be slightly smaller than the wooden rim circumference. The band was heated until it expanded, placed over the rim, and allowed to cool. As it cooled, it contracted, shrinking tightly onto the rim and compressing the wood. This compression actually strengthened the rim by forcing the wooden segments tightly together. The iron tire protected the wheel from wear, prevented the rim from splitting, and improved traction. The harder surface meant wheels lasted far longer. A wooden wheel might need replacement after months of heavy use, while an iron-tired wheel could last years. The improved durability was economically transformative. Carts became long-term investments rather than consumables, changing the economics of trade and transportation. Iron also enabled new wheel designs. With iron reinforcement, wooden components could be made lighter and more delicate while maintaining strength. This allowed for more elegant spoked wheels with thinner, more numerous spokes. Celtic wheels from the Iron Age often featured sophisticated iron fittings, not just rim bands but spoke reinforcements, hub bands, and decorative elements demonstrating how metallurgy and woodworking arts advanced together. The techniques for working different materials shaped wheel design. Bronze, being castable, allowed for complex shapes but was expensive. Iron, being forgeable, required heating and hammering but was cheaper and harder. Wood, being carvable, offered flexibility in design but had inherent limitations. Master wheelwrights needed expertise in all three materials, understanding how to combine them optimally. The material used also affected maintenance. All wood wheels required frequent lubrication of bearing surfaces with animal fats or plant oils. Bronze components needed less frequent lubrication, but could corrode if exposed to salt or certain chemicals. Iron required protection from rust. Wheelwrights learned to paint or oil iron components regularly. Different materials demanded different care regimens. Regional variations emerged based on available materials. Areas with good timber but limited metal continued using primarily wooden wheels longer. Regions with active metalworking industries adopted metal reinforcement earlier. Trade networks meant materials could travel. Lebanese cedar was prized for chariot construction across the Mediterranean, while bronze and iron moved along the same trade routes. But local materials still dominated most wheel construction. The interaction between material science and wheel design demonstrates how technological systems evolve. Better materials enabled new designs, which created demand for even better materials, which enabled further improvements. This positive feedback loop drove continuous innovation across centuries. Bronze Age chariot wheels represent a pinnacle of wood and metal construction. Egyptian chariots from Tutankhamun's tomb show six-spoke wheels with steam-bent felloes, rim segments, sophisticated joinery, and bronze fittings. The craftsmanship required hundreds of hours per wheel, but the result was a masterpiece of materials engineering. Light, strong, fast, and beautiful. Roman wheels demonstrated Iron Age sophistication. Iron tires were standard. Hubs were reinforced with iron bands, and some designs incorporated bronze bushings for smooth rotation. The Romans also developed iron-shod wheels for their extensive road network. The hard iron tires worked well on stone paving. Roman engineering treatises described wheel construction in detail, codifying knowledge that had been primarily traditional craft knowledge. Chinese wheelwrights developed distinctive approaches to materials combination. They often used multiple wood species in a single wheel, harder woods for hubs and spokes, more flexible woods for felloes. This required understanding each wood's properties and how they worked together. Chinese wheels sometimes featured intricate joinery that required no metal fasteners, demonstrating woodworking sophistication equal to any contemporary metalworking. The medieval period saw further refinements. Ironworking techniques improved, allowing for more precise manufacture of metal components. Some wheels featured full iron spokes rather than wooden ones, heavier but nearly indestructible. Water wheels and windmill wheels used these heavy iron constructions, trading weight for durability in stationary applications, where mass didn't matter. The principle underlying materials evolution was constant. Use the best material you can afford for each component based on its requirements. Hubs needed strength, use oak reinforced with iron bands. Spokes needed toughness and lightness, use ash or elm with bronze or iron fittings at stress points. Rims needed wear resistance, use hard wood with iron tires. Bearing surfaces needed smoothness and durability, use bronze or iron bushings with regular lubrication. This componentized thinking, treating the wheel as a system of parts, each optimized separately, represents sophisticated engineering even before formal engineering disciplines existed. It's the same approach used in modern manufacturing, where different materials optimize different functions within a single product. The evolution from wood to bronze to iron wheels paralleled broader metallurgical development, but it also drove demand for better metals. The market for wheel components created incentives for improving metallurgy. Better wheels enabled better transportation, which expanded trade networks, which increased access to metals, which enabled still better wheels. Technology, economy, and material science advanced together, each driving the others. Today, wheels are made from advanced alloys, composites, rubber, and plastics, materials ancient wheelwrights couldn't have imagined. But the principles remain the same. Choose materials that optimize each component's function. Combine materials to leverage their complementary properties. And understand that material selection is as important as design. The wooden wheels that first rolled across Mesopotamia 5,500 years ago taught these lessons, and we're still learning from them. Chapter 11. The wheel's endless reinvention. Stand in any modern city and count the wheels. Car wheels, obviously. Bicycle wheels. Skateboard wheels. Wheels on suitcases, office chairs, shopping carts, baby strollers. Inside buildings. Gears, pulleys, turbines, all variations on rotary motion. The potter's wheel that started it all 5,500 years ago has spawned countless descendants, each adapted for specific purposes, each demonstrating the wheel's fundamental versatility. The basic principle, a circular object rotating on an axle, has been endlessly reinvented because it solves so many different problems. Transportation was just the beginning. Once humans understood rotary motion, they found applications in every domain of life. The wheel didn't just transform transportation. It became the basis for mechanical civilization. Consider the gear wheel, appearing around 300 BCE in Greek and Chinese machinery. A gear is essentially a wheel with teeth around its circumference, designed to mesh with other gears. This simple addition created mechanical advantage. A small gear driving a large gear multiplies force but reduces speed, while the reverse multiplies speed but reduces force. Gears enabled precision machinery, mechanical clocks, and eventually, the Industrial Revolution's complex automated systems. The water wheel represents another radical reinvention. Instead of wheels moving vehicles, water wheels stayed in place while flowing water moved them. This converted the kinetic energy of moving water into rotational energy that could power machinery. By the Middle Ages, water wheels drove not just grain mills, but sawmills, textile manufacturing equipment, bellows for forges, trip hammers for metalworking, and numerous other industrial processes. Some historians argue that water wheels represented Europe's first industrial revolution, occurring centuries before steam power. The windmill, developed around 600 CE in Persia and spreading across Europe by the 12th century, applied the same principle to air movement. Windmill sails were essentially wheels with blades optimized to catch wind. The rotational energy powered mills, pumps, and other machinery. Dutch windmills famously pumped water to drain land for agriculture, literally creating new land through the application of wheel technology. The spinning wheel, appearing around 1000 CE, transformed textile production. By using a large wheel to drive a small spindle through gears or belts, spinners could produce thread far faster than with traditional hand spindles. This dramatically reduced thread costs, making cloth more affordable and enabling the later textile industry that drove the Industrial Revolution. A wheel designed for making pottery had, through multiple reinventions, enabled the transformation of clothing production. The clock represents one of the wheel's most precise applications. Mechanical clocks, developed in medieval Europe around 1300 CE, used intricate gear trains, complex arrangements of wheel-shaped gears to convert the regular motion of a falling weight or oscillating pendulum into precise time measurement. The mathematics of gear ratios allowed clockmakers to create mechanisms that tracked hours, minutes, and eventually seconds with remarkable accuracy. Time itself became standardized through the application of wheels. The Industrial Revolution was fundamentally a revolution in wheel technology. Steam engines converted linear piston motion into rotary motion through wheels called flywheels, which smoothed out power delivery and stored energy. This rotary motion drove factory machinery through complex systems of wheels, gears, belts, and pulleys. Factories were forests of turning wheels, each connected to others in elaborate mechanical networks. The wheels that had started by moving carts were now powering civilization's industrial transformation. The railway wheel deserves special mention. Railway wheels, appearing in the early 1800s, featured a flange design, a rim with an inner edge that kept the wheel on the track. This seemingly simple innovation enabled reliable rail transport, which revolutionized commerce and passenger travel. The flange was a wheel innovation that made modern transportation networks possible. Railway gauge, the distance between tracks, often traced back to ancient cartwheel widths, showing continuity across millennia of wheel evolution. The bicycle wheel, invented in the mid-1800s, represents another radical redesign. Wire-spoke wheels, with dozens of thin metal spokes under tension rather than thick wooden spokes in compression, created wheels that were simultaneously incredibly light and remarkably strong. The same wire-spoke technology later enabled early automobiles and aircraft landing gear. A wheel design developed for human-powered transport enabled powered vehicles through its superior strength-to-weight ratio. The pneumatic tire, invented in 1888, transformed wheels once again. Inflatable rubber tires provided cushioning, traction, and shock absorption impossible with solid wheels. This innovation made bicycles comfortable, automobiles practical, and eventually enabled aircraft to land safely. The ancient wheelwrights' iron tire bands had evolved into sophisticated rubber compounds reinforced with fabric and steel, optimized for different conditions and purposes. The 20th century brought wheels into new realms. Turbine wheels, essentially wheels designed to be driven by steam, water, or gas flow, became the hearts of power plants, generating most of the world's electricity. Jet engines and rocket turbines use the same principle at extreme temperatures and speeds. The wheel that had first turned clay now propelled aircraft and spacecraft. Computer hard drives feature spinning disks, essentially wheels holding magnetic data. Before solid-state drives, these spinning platters stored the world's digital information. Even in an electronic age, rotary motion remained crucial for data storage. The potter's wheel had, through countless iterations, become part of the information revolution. The wheel principle appears in unexpected places. Rotating drums in washing machines and dryers. Centrifuges that separate materials by spinning them. Gyroscopes that help navigate ships and spacecraft. Flywheels that store energy in modern hybrid vehicles. Even the human-powered hamster wheel has modern equivalents in exercise. Equipment treadmills and stationary bicycles that turn human muscle. Power into rotary motion for fitness. Medical. Technology uses wheels extensively. CT scanners rotate X-ray sources around patients. Centrifuges separate blood components. Dental drills spin at extreme speeds. Physical therapy equipment uses wheel-based resistance systems. The principle discovered by ancient potters now helps diagnose and treat disease. Modern manufacturing relies on wheels at every stage. Cutting wheels, grinding wheels, polishing wheels. Conveyor rollers moving products through assembly lines. Robotic arms with rotary joints. CNC machines using wheel-shaped cutters with precision measured in microns. The industrial world turns on wheels, literally and figuratively. Even digital technology shows wheel influence. Many computer interfaces use scroll wheels to navigate, though nothing physically rotates. The metaphor of rotation remains useful. Control systems use virtual dials and knobs, digital representations of physical wheels. The concept is so fundamental that even when we've transcended physical limitations, we still think in terms of rotation and turning. The wheel's endless reinvention demonstrates a profound truth about innovation. Fundamental principles can be adapted infinitely. The same basic idea rotation around an axis solved problems, from shaping clay to measuring time to generating electricity to storing data. Each reinvention built on previous innovations while adapting to new needs and contexts. This pattern continues today. Modern wheels incorporate materials ancient wheelwrights never imagined: carbon fiber, advanced polymers, smart materials that change properties based on conditions. They're designed using computer modeling that simulates forces and stresses with precision impossible before. They're manufactured with automation and quality control that ensures consistency. Yet they're still recognizably wheels, still based on principles discovered thousands of years ago. The potter's wheel that started this journey 5.5 millennia ago has been reinvented thousands of times. Each iteration optimized for different purposes, materials, and technologies. From clay to time to transportation to power generation to data storage, the wheel has adapted to every challenge humans have faced. And it continues adapting. Future wheels will likely incorporate technologies we haven't yet invented, solving problems we haven't yet encountered, enabling applications we haven't yet imagined. The wheel's story isn't finished. It's still being reinvented, still finding new applications, still turning at the heart of human civilization. That original Mesopotamian innovation, making something spin, proved to be one of the most generative ideas in human history, spawning endless variations and applications. The wheel keeps turning, keeps reinventing itself, keeps driving progress. And it will continue doing so as long as humans keep asking, what else can we make go round? The 21st century has brought perhaps the most radical reinvention of the wheel yet. the transformation from physical object to digital metaphor and virtual tool. In the world of user interface design, the wheel persists as a fundamental organizing principle, even when nothing actually rotates. The scroll wheel on your computer mouse translates finger movement into the ancient concept of rotation, even though the mechanism might use optical sensors rather than actual spinning. Touch screens respond to circular gestures we call rotating, our fingers tracing invisible wheels in the air. This digital persistence reveals something profound. The wheel isn't just a physical device, but a cognitive tool, a way of thinking about control, navigation, and interaction. When software designers create volume controls, they instinctively make them circular dials. When game developers design steering interfaces, they default to wheels. When architects of virtual reality need to represent rotation or adjustment, they reach for the wheel metaphor. 5,000 years after its invention, the wheel remains our default mental model for controlled, continuous change. Space exploration has pushed wheel technology into environments its inventors never imagined. The Mars rover's Spirit, Opportunity, Curiosity, and Perseverance roll across alien landscapes on wheels specifically engineered for Martian conditions. These wheels face challenges unknown Earth: abrasive volcanic rock that shreds rubber, temperature extremes from -100 degrees Celsius to +20 degrees Celsius, and gravity only 38% of Earth's. The solution? Wheels made of aluminum or titanium with clever tread patterns, some even capable of deforming and reforming to navigate obstacles. The Perseverance rover's wheels incorporate lessons learned from predecessors. Each wheel is machined from a single block of aluminum, featuring a pattern of curved tread elements that provide traction while preventing rocks from getting wedged. They're simultaneously wheels, suspension components, and sensors. Strain gauges embedded in the wheels measure forces, helping the rover navigate safely. The ancient Mesopotamian potter who spun clay never imagined their innovation would one day roll across another planet. But the principle remains identical. Rotation enabling movement. Space stations use a different wheel, application momentum wheels or reaction wheels, that enable spacecraft to orient themselves without expelling propellant. By spinning massive wheels and then changing the rotation speed, spacecraft can rotate themselves using the conservation of angular momentum. The International Space Station maintains its orientation using 4 massive control moment gyroscopes, essentially wheels within wheels that provide precise attitude control. The potter's wheel that discovered rotation now keeps billion-dollar space stations properly aligned as they orbit Earth. The wheel has been reinvented at scales invisible to the eye. Molecular machines, nanoscale devices built from individual molecules, include wheel-like rotating components. In 2016, the Nobel Prize in Chemistry was awarded for the design and synthesis of molecular machines, including molecular motors that feature rotating elements. These nanowheels consist of carefully designed molecules that rotate in response to light or chemical signals, potentially enabling drug delivery systems that can navigate within the human body or molecular assembly lines, building materials atom by atom. Even more remarkably, nature itself invented molecular wheels. The bacterial flagellum, the rotating tail that propels bacteria, features a rotary motor at its base. This biological wheel, evolved over billions of years, operates on principles similar to macroscopic wheels. A rotor turns within a stator, powered by the flow of protons rather than oxen or engines. Biology and technology converged on the same solution: rotation as the key to efficient motion. As we stand in the early 21st century, surrounded by turning wheels from the nano to the astronomical scale, an intriguing question emerges. Have we finally exhausted the wheel's potential for reinvention? Or are we merely at another beginning? Emerging technologies suggest the latter. Magnetic levitation creates wheels that never touch the ground, eliminating friction almost entirely. Omnidirectional wheels, spherical or roller-based designs that can move in any direction without turning, are reimagining mobility for robots and vehicles. Smart wheels with integrated sensors, processors, and motors are becoming autonomous systems that don't just follow instructions, but make decisions. The next frontier might be wheels that adapt in real time to conditions, changing their properties moment by moment. Imagine wheels that can alter their diameter, stiffness, or tread pattern instantly based on terrain. Material science is developing programmable matter that could make such adaptive wheels possible. Or consider wheels that harvest energy as they turn, converting motion into electricity to power the vehicles they support. Some futurists envision post-wheel transportation, magnetic levitation, anti-gravity, or other principles we haven't yet mastered. But if history teaches us anything, it's that the wheel is endlessly adaptable. Even if we develop radically new transportation methods, the principle of rotation will likely remain essential in other applications. The wheel has survived every technological revolution for 5,500 years by continually finding new purposes, new forms, new contexts where rotation solves problems. The wheel's greatest achievement isn't any single application, but its conceptual fertility, its ability to be endlessly reimagined, continuously adapted, perpetually reinvented. From shaping clay to propelling Mars rovers, to controlling spacecraft orientation to enabling molecular machines, the wheel has proven that truly fundamental ideas never become obsolete. They just keep turning, keep evolving, keep rolling forward into whatever future we create. The first reinvention happened in a Mesopotamian pottery workshop. The most recent might be happening right now in a laboratory or workshop somewhere. As someone asks once again, what else can we make go round? 5,500 years have passed since that first potter sat before a spinning disc and shaped clay with unprecedented precision. The journey from that moment to today's world, where wheels turn in billions of devices, driving everything from transportation to power generation to data storage, is one of continuous innovation, adaptation, and reinvention. The story of the wheel's invention reveals fundamental truths about human innovation. It wasn't a single flash of genius, but a process of accumulated insights. The potter's wheel came first, demonstrating the principle of rotation. Centuries later, someone made the conceptual leap to turn that spinning disc 90 degrees and use it for transportation. The axle was added, solving the challenge of controlled rotation. Solid wheels gave way to spoke designs as engineering sophistication increased. Materials evolved from wood to bronze to iron to modern alloys. Each step built on previous innovations. The wheel also teaches us that innovation is contextual. The same technology that transformed Mesopotamian transportation was rejected by sophisticated civilizations in the Americas. Not from ignorance, but from rational assessment that wheels didn't fit their needs and conditions. Technology adoption isn't about intelligence or advancement. It's about matching tools to context. We've seen how the wheel spread selectively across cultures, adapted and reinvented by each society that adopted it. Egyptian chariots, Chinese wheelbarrows, Celtic iron-rimmed wheels. Roman engineering, each culture made the wheel their own, optimizing it for their purposes. The diffusion of wheel technology wasn't simple copying, but creative adaptation. The wheel's impact extended far beyond its obvious transportation applications. Water wheels mechanized agriculture and industry. Gear wheels enabled precision machinery. Grinding wheels processed food. The principle of rotation became fundamental to mechanical civilization, appearing in countless applications from ancient times to the present. Perhaps most remarkably, the wheel demonstrates that the simplest ideas can be the most powerful and enduring. A circle rotating on an axle is geometrically and mechanically simple. Yet from that simplicity came infinite complexity, all the variations, applications, and innovations that have made wheels central to human civilization for thousands of years. The ancient wheelwrights of Mesopotamia, China, Egypt, and Europe couldn't have imagined where their innovations would lead. They solved immediate problems, shaping pottery more efficiently, moving cargo more easily, traveling faster, grinding grain, lifting water. But in doing so, they established principles and created technologies that will be endlessly adapted and reinvented. Today, wheels are so ubiquitous we rarely notice them. We take for granted that cars have wheels, that we can roll suitcases through airports, that gears turn inside our devices, that turbines generate our electricity. This ubiquity is testament to the wheel's fundamental utility. It solves so many problems so well that it became invisible through familiarity. Yet understanding the wheel's history, the centuries of development from potter's wheel to transportation wheel, the engineering challenges solved, the materials evolution from wood to advanced alloys, the cultural context that shaped adoption or rejection, reveals that what seemed simple was actually profoundly innovative. Each advance required observation, experimentation, accumulated knowledge, and creative problem-solving. The wheel reminds us that innovation is iterative. The first wheels were crude wooden discs. Over millennia, they evolved into sophisticated devices optimized for countless purposes. Each generation of wheelwrights built on predecessors' knowledge, making incremental improvements that compounded into revolutionary change. Progress isn't always dramatic breakthrough, often it's patient, persistent refinement. The wheel also shows how technology and society co-evolve. Wheels enabled trade networks, which created demand for better wheels, which enabled longer distance trade. Chariots changed warfare, which created demand for faster chariots, which drove innovations in wheel design and horse breeding. Agricultural applications increased food production, supporting larger populations, creating demand for more agricultural equipment. Technology shapes society, which shapes technological development in ongoing feedback loops. Looking forward, the wheel continues evolving. Modern wheels incorporate materials and manufacturing techniques impossible in earlier eras. They're optimized using computer simulation, manufactured with precision, embedded with sensors, adapted for new applications. Yet they're still recognizably wheels, still using principles discovered thousands of years ago by anonymous potters and wheelwrights. The wheel's story is ultimately humanity's story. A story of solving problems creatively, building on previous knowledge, adapting innovations to new contexts, and continuously improving our tools and techniques. That Mesopotamian potter who first spun clay on a disc couldn't have known they were starting a revolution that would still be rolling 5 millennia later. But in that moment of innovation, when hands shaped spinning clay and proved that rotation could accomplish what static methods couldn't, they set wheels in motion literally and figuratively that would carry human civilization forward through all the ages since. The wheel keeps turning. In transportation, industry, power generation, data storage, and countless other applications, wheels spin, drive, rotate, and enable the modern world. And somewhere, right now, someone is probably reinventing the wheel yet again, finding a new application, a new optimization, a new way to harness the power of rotation. Because that's what humans do. We take fundamental principles and adapt them endlessly, solving new problems with old ideas made new. The first wheels were invented 5,500 years ago, but the wheel's invention never really ended. It continues today, will continue tomorrow, and will keep rolling into whatever future we create. The circle that changed the world is still turning, still innovating, still teaching us that the simplest ideas, when truly understood and creatively applied, can be the most powerful and enduring of all.